Right now, a spacecraft is transmitting data from the edge of everything we know. Not metaphorically, literally right now. As you watch this, Voyager 1 is alive, moving and sending signals home on 22 watts of fading plutonium power. 22 watts. That's less than most bathroom light bulbs, and it's enough to reach us across nearly 16 billion miles of open space. The signal you're benefiting from left that spacecraft 23 hours and 32 minutes ago. In 3 months, that delay crosses a full day for a single message to arrive. And Voyager, after almost 50 years, may not have many years left to send them. Here's what makes that urgent. The data arriving right now is the strangest Voyager has ever transmitted. A wall of fire that shouldn't exist. A ghost hum from the silence between stars. A magnetic alignment that broke every model we had. The textbooks said this place would be quiet. It isn't. Let's put some numbers on the table, because the scale here is the kind that makes the brain quietly refuse to cooperate. Voyager 1 is currently approximately 25.4 billion kilometers from Earth. That is not the farthest any probe has traveled in a movie. That is the farthest any human-made object has ever traveled in the history of our species, confirmed by NASA's Jet Propulsion Laboratory's live tracking system. Nothing we have ever built has gone farther. On November 18, 2026, at 2:16:07 in the morning Pacific Time, it will cross exactly 1 light day from Earth. JPL has calculated that moment to the precise second. From that point on, a single command sent from Mission Control will require a full 24 hours just to arrive. No spacecraft has ever been that far, ever. And the machine doing this? Its onboard computers hold 69.63 kilobytes of memory, less than a single photograph on your phone. Its transmitter puts out 22 watts, a dim desk lamp. And yet the Deep Space Network's massive antenna dishes, straining near the absolute limits of their sensitivity, still pull its signal out of the dark across 16 billion miles. A machine this old, this weak, transmitting from this far, and it's still sending back data that is actively rewriting the textbooks. Here's how we got here. September 5th, 1977, Kennedy Space Center. A rocket climbs away from Florida carrying a spacecraft the size of a small car built by hand, loaded with 1970s technology and aimed at the outer planets. The mission plan was straightforward. Fly past Jupiter, fly past Saturn, collect data, done. Engineers estimated maybe 5 years of useful life. Nobody seriously planned for what came after. But before Voyager 1 left, someone made sure it was carrying more than instruments. Bolted to its frame was a golden copper disc, Carl Sagan's golden record. On it, 116 images of Earth and its life, greetings spoken in 55 languages, and 90 minutes of music ranging from Beethoven to Chuck Berry. It was a message to whatever or whoever might someday find it. An act of extraordinary optimism from people who knew the probe would almost certainly never be found at all. By 1981, Voyager 1 had done its job. Jupiter, Saturn, done. Most missions end there. This one didn't. JPL quietly pivoted, extending the mission outward, and a small team of engineers began what became one of the longest continuous spacecraft operations in history. Decades passed. The engineers who built Voyager aged, some retired, some died. The probe kept going, and a new generation took over the task of nursing a machine that was never designed to still be running. The scientific question driving that extended mission was this: where does the sun end? The sun doesn't just emit light, it exhales. Constantly, a stream of charged particles called the solar wind blows outward in every direction, inflating a vast magnetic bubble around our entire solar system. That bubble is called the heliosphere, and at some point the models said it had to stop. Theorists predicted the edge. The heliopause would be a relatively calm transition zone. Solar particles would gradually thin out. Cosmic rays from deep space would gradually filter in. Interstellar space would begin the way a tide comes in, slowly, smoothly, predictably. On August 25, 2012, at 121.7 astronomical units from the Sun, Voyager 1 reached that boundary and crossed it, becoming the first human-made object to enter interstellar space. What actually happened at that boundary, and what Voyager found on the other side, was nothing like the quiet the models promised. The models expected a gradual fade. What Voyager recorded was a wall. As the spacecraft approached and crossed the heliopause, its instruments measured plasma temperatures of 30,000 to 50,000 Kelvin. That's between 54,000 and 90,000 degrees Fahrenheit, compressed into a violent superheated zone where the solar wind slams into interstellar gas and neither side wins cleanly. Scientists began calling it, informally, the Wall of Fire. Not a poetic exaggeration, a literal description of what the data showed, a blazing frontier at the edge of our solar system that no physics textbook had predicted with anything close to this intensity. Stop and sit with that for a second. 90,000 degrees Fahrenheit, at the boundary of our solar system. Voyager survived it, and the reason why is one of the stranger facts in this entire story. Temperature and heat are not the same thing. The plasma at the heliopause is extraordinarily hot, meaning its particles carry enormous individual energy. But it is also extraordinarily sparse. There are so few particles that almost none of them actually contacted the spacecraft in a meaningful way. Voyager slipped through a wall of fire, the way a person walks through a cloud of steam so thin it leaves no mark. The zone is produced by magnetic reconnection. The solar magnetic field and the interstellar magnetic field snapping together and realigning, releasing bursts of energy in the process. Violent, beautiful, and completely absent from the models. Then came the second thing, the alignment anomaly. When Voyager 1 crossed the heliopause, its magnetometer recorded something that made scientists pause. The magnetic field just outside the boundary, in interstellar space, was running parallel to the magnetic field just inside it within the heliosphere. That shouldn't happen. The Sun's field and the galaxy's field have no obvious reason to align. Researchers noted it but stayed cautious. One data point, one crossing. Maybe a coincidence. Then Voyager 2 crossed the heliopause from a different direction entirely, and its magnetometer found the same thing. NASA confirmed it directly, stating that Voyager 2's observations confirmed the Voyager 1 finding and indicated that the two fields align. No existing model predicted it. None. The boundary between our solar system and interstellar space is magnetically coherent in a way that current physics cannot fully explain. And then the third discovery arrived. Quieter than the others, and in some ways, the most unsettling. On May 10, 2021, Cornell astronomer Stella Koch-Ocker and her colleagues published a paper in Nature Astronomy, reporting something Voyager 1's plasma wave system had been detecting for years, without anyone fully recognizing what it was: a faint, persistent, narrowband hum, not triggered by a solar flare, not caused by a shockwave, just there. A constant, low-level vibration in the interstellar plasma itself. Ocker described it as the faint, persistent hum of interstellar gas. The space between the stars, which science had characterized for decades as silent and empty, has a voice. It has always had one. We just needed a 46-year-old spacecraft running out of power to finally hear it. 3 discoveries: a wall of fire, a magnetic impossibility, and a voice from the void, all returned by a probe that has now powered down 8 of its 10 instruments and is running out of time. But Voyager 1 is only one data point. What happened when its twin crossed the same boundary from a completely different direction? Voyager 1 crossed the heliopause in August 2012. Voyager 2 crossed it on November 5, 2018. 6 years later, from a different solar latitude, and at a measurably shorter distance from the Sun. NASA noted this directly, confirming it was consistent with the two probes encountering the heliopause at different distances, same boundary, different entry points. And what the comparison revealed didn't simplify the picture, it tore it open. If the heliopause were the clean, uniform shell the models envisioned, two probes crossing it from different angles should tell roughly the same story. They didn't. The wall of fire that Voyager 1 recorded had a different thickness and pressure profile than what Voyager 2 encountered. The boundary flexes. It bulges and compresses depending on where you approach it, shaped by forces the models hadn't fully accounted for. The edge of our solar system is not a sphere. It is something lopsided, dynamic, and alive in ways that only became visible once we had two sets of eyes out there instead of one. But the thickness discrepancy wasn't the most disturbing part. Voyager 2's instruments detected leakage. A 2019 NASA JPL report confirmed it. The heliopause is permeable. Galactic cosmic rays, high-energy particles born from supernovae and other violent stellar events across the galaxy, are leaking inward through the boundary's flanks, and solar particles are leaking outward the other way. The bubble we assumed was sealed is punctured. The most remote regions of the heliosphere are exchanging material with interstellar space in a constant, unmodeled bleed in both directions. Both probes also registered higher than expected plasma density on both sides of the crossing, which tells scientists something significant. Interstellar pressure is not passive. It is actively pushing back against the heliosphere, compressing and reshaping its outer layers in real time, in ways that no pre-Voyager model had calculated. The heliosphere isn't just sitting there, it's being squeezed. Here is what makes this escalate rather than resolve. You might expect that two data points would bring clarity, that the second crossing would confirm the first, explain the anomalies, and give scientists a complete picture to work with. Instead, the second crossing confirmed every mystery the first one raised and added new ones. Two different pressure profiles, two different boundary thicknesses, and yet the same impossible magnetic alignment at both locations. The internal and external fields, running parallel in a way that physics has not yet explained, present at both crossings, regardless of angle or distance. The contrast doesn't close the case, it doubles it. What Voyager has revealed, collectively, is that the edge of our solar system is not a wall, it is not a membrane, it is a dynamic, asymmetric, semi-permeable frontier, one that shifts under pressure, leaks in both directions, burns at temperatures no model predicted, hums with a voice no one knew it had, and aligns its magnetic fields in a pattern that current theory cannot account for. And we know all of this because two spacecraft launched in 1977 on 5-year missions are still, improbably, out there. Now here's the part that almost no one is talking about. What all of this means for every single person on Earth right now, whether they ever think about space or not. The heliosphere is not just a scientific curiosity. It is a shield. The same magnetic bubble whose edge Voyager has been mapping is the primary barrier standing between Earth's biosphere and the full force of galactic cosmic rays, high-energy particles produced by supernovae, colliding neutron stars, and other catastrophic events scattered across the galaxy. These particles damage DNA. In sufficient quantities, they increase cancer rates. The heliosphere absorbs and deflects the majority of them before they ever reach us. Voyager has now confirmed that the boundary of that shield leaks. That finding doesn't mean Earth is in immediate danger. The leakage occurs at the distant flanks of the heliosphere, far from our planet, and scientists are still working to understand its scale and significance. But it raises a question that nobody had to seriously ask before Voyager provided the data to ask it. How much protection are we actually getting? The shield we assumed was sealed has holes. Quantifying those holes, understanding how they shift with solar activity, and modeling what they mean for long-term exposure on Earth. That work is now underway, and it only exists because Voyager went out there and looked. Which brings us to what is happening right now in 2026, and why it is urgent in a way that has nothing to do with abstract physics. On April 17, 2026, NASA powered down Voyager 1's low-energy charged particles experiment, an instrument that had run nearly without interruption for almost 49 years, because the probe no longer had enough power to keep it alive. Voyager mission manager Kareem Badaruddin said it plainly: while shutting down a science instrument is not anybody's preference, it is the best option available. 2 instruments now remain on Voyager 1, 2 from an original 10. Engineers at JPL are preparing to attempt something they have quietly nicknamed the Big Bang, a simultaneous swap of multiple power-consuming devices for lower-power alternatives, executed all at once from 16 billion miles away with no margin for error. On August 4, 2026, JPL confirmed the procedure had been successfully carried out on Voyager 2, buying that probe at least 1 more year of scientific operation. Voyager 1's attempt is coming next. If it fails, the instruments that go dark permanently. There is no repair mission. There is no backup probe. Voyager 1 is the only human-made object operating in interstellar space, measuring an environment that no other machine can reach, and every remaining instrument on it is irreplaceable. And there's a larger reason to care about whether Voyager survives, because what it's measuring is something no other machine can measure, from a vantage point no other machine can reach. The plasma hum that Stella Koch-Ocker's team identified isn't just a strange sound from deep space. It is something with immediate scientific consequence, something that changed what is actually possible in interstellar research. Before the hum was discovered, scientists could only measure the density of interstellar plasma when the sun cooperated. A large solar flare would fire a shockwave outward through space. That shockwave would disturb the plasma around Voyager, and the probe's instruments would briefly register the disturbance. It was the only method available. Useful, but entirely dependent on waiting for the sun to do something dramatic. Cornell astronomer Shami Chatterjee put it directly: now we know we don't need a fortuitous event related to the sun to measure interstellar plasma. The hum is always there, which means the measurement is always possible. What that continuous signal has already revealed is striking on its own terms. Ocker's team found that the electron density around Voyager 1 rose roughly 40-fold between 2013 and 2015. A dramatic increase suggesting the probe had entered a distinctly denser pocket of interstellar gas. No model had predicted that pocket. No theory had placed a structure like it in that region of space. Voyager didn't just find a hum. It found, embedded in that hum, evidence of large-scale interstellar architecture that we didn't know existed. That data is now feeding directly into the design of future interstellar probes. Craft with better instruments, more sensitive sensors, and operational lifespans built around what Voyager taught us about what actually waits beyond the heliopause. The path forward is being drawn using a map that only exists because a 1970s machine stayed alive long enough to make it. And now consider what staying alive actually means for Voyager in 2026. On November 18th at 2:16 in the morning Pacific time, the probe will cross 1 full light day from Earth, the first spacecraft in history to reach that distance. At that point, a command sent from JPL takes 24 hours to arrive. A response takes another 24 hours to return. A single exchange takes 2 full days. Engineers must increasingly build Voyager's operations around autonomy, around decisions the spacecraft makes on its own time, because there is no longer any such thing as a quick correction from home. The probe carrying Carl Sagan's golden record, his message to the stars, is now so far away that it must, in a very real sense, think for itself. It is aimed toward the constellation Ophiuchus. Its closest approach to another star, Gliese 445, will not occur until approximately the year 40,272. By galactic standards, Voyager 1 has barely left the driveway, which brings us to the question that no one in 1977 thought they would be asking in 2026. What do we do if Voyager falls silent before it finishes telling us what's out there? Here is what we are actually talking about. A machine with 69.63 kilobytes of memory, less than a single photograph on your phone, has produced discoveries that will reshape physics textbooks for generations. A wall of fire burning at 50,000 Kelvin that no model placed there. A magnetic alignment that current theory cannot explain. A persistent hum from the interstellar medium that proved the space between stars is not silent, has never been silent, and was only waiting for something sensitive enough to listen. Voyager 1 did all of this on 22 watts, the output of a dim lamp, running on technology older than the internet, older than the personal computer, older than most of the engineers now fighting to keep it alive. Somewhere between 15 and 16 billion miles from Earth, in a region that scientists described for decades as empty and predictable, humanity's most distant ambassador is still transmitting, still humming, still surprising everyone who thought they knew what was out there. It carries Beethoven, it carries Chuck Berry, it carries the sound of rain falling on Earth, and greetings spoken in 55 human languages, pressed into a golden copper disc by people who understood that the most honest thing they could do was send something beautiful into the unknown and hope. That disc is still out there. It will be out there long after Voyager's last instrument goes dark, long after every person who built it is gone, drifting silently toward a star it won't reach for another 38,000 years. The Big Bang procedure is the last engineering lifeline. If it works on Voyager 1 the way it worked on Voyager 2, the probe may keep transmitting into the late 2020s. If it doesn't, the final signal from the most distant object our species has ever built could arrive before this decade ends. Either way, it doesn't diminish what Voyager has already done. The map is permanently changed. The silence has a voice. And a dim lamp in the dark between stars is still, against every reasonable expectation, shining. Before you go, one question, and I want you to actually answer this one in the comments, because the answers are going to be remarkable. If you could add one thing to Voyager's golden record that isn't already on it, one sound, one image, one piece of music, one moment from human life on Earth, what would you choose and why? Not what you think should be there in some official sense. What you would put there. What you'd want a universe to know about us. Leave it below. Read what other people wrote. This comment section is going to be worth your time, and if this story isn't finished for you, it isn't finished for us either. NASA's Big Bang procedure worked on Voyager 2. Voyager 1 is next. We will be covering that attempt the moment it happens, because this is a mission that does not get a second chance. If the fix fails, it fails permanently. Hit subscribe so you're here when that story breaks, because right now, at this exact moment while you're reading this, while the comment section fills, while engineers at JPL run their calculations, Voyager 1 is still out there, still transmitting, still humming, still sending back data from a place every physics textbook said would be silent. It isn't silent. It never was. When Voyager 1 launched in 1977, its radioisotope thermoelectric generator was producing approximately 470 watts of power. It loses roughly 4 watts every year. Do that math across 49 years, and you understand exactly why JPL is performing surgery on a spacecraft from 16 billion miles away. The goal now is surgical preservation. JPL's team hopes to keep Voyager, one's cosmic ray subsystem and magnetometer operational for as long as physically possible. effectively converting both Voyager probes into permanent weather stations for interstellar space, sensing and reporting the environment as they drift deeper into it. Before the mission's 50th anniversary in 2027, additional instruments on both spacecraft will almost certainly need to go offline. The countdown is real. What comes after Voyager is already being designed. Engineers and scientists studying the proposed interstellar probe concept at Johns Hopkins Applied Physics Laboratory are using Voyager's data as their foundational baseline. The wall of fire measurements, the plasma hum density maps, the magnetic alignment findings, building the next generation of deep space exploration on everything this fading, extraordinary machine taught us first.